Okay, we are now going to apply this general theory on the Diriclet problem. Let us just recall the following important aspects of the Diriclet problem. First, and this is in fact very general for all type of problems we are going to discuss in this course. We have some strong formulation which is known from the classical theory how to solve, and this strong formulation is just a partial differential equation. On the left side, a partial differential operator, which is, for example, a second order operator. That means that we differentiate twice with respect to the spatial coordinates, and on the right side we have some function f, which in the case of Poisson problem is some kind of heat source, for example. So this is a typical strong formulation or general strong formulation, and this formulation is in most cases equivalent with the weak formulation. That means that if we find the solution of this strong formulation, we also have that this solution is a solution to the weak formulation, and vice versa. This is not always the case, but for most interesting cases we are going to consider, which are interesting with respect to from an engineering point of view, these two formulations will be equivalent. Moreover, we have that this weak formulation is also equivalent with some minimum formulation if the conditions 1, 2, 3, and 4 are satisfied. And these 4 conditions have been discussed in a previous lecture. So this minimum formulation took the following form. We have that f of u, the solution u, must be less than f of v for all v element in some Hilbert space capital V, where f of v is always equal to this. Now we are going to use this general theory to solve or to prove the existence of solutions of the Diriclet problem. And then we have to go through all these points in order to verify that they are satisfied. So we have an open bounded set in Rn here, and this is a region omega with some boundary, and this boundary is assumed to be sufficiently smooth. For the Diriclet problem, we have that u should be equal to 0 on the boundary. So we are using also test functions phi, which are 0 on the boundary. And the space we are going to consider then is just the space W0. Moreover, we have this L of phi, which is equal given by this integral. F is in this Lebesgue space L2, and we recall that the weak formulation took this form, that A of u phi is equal to L of phi for all. This symbol means for all phi in this subular space W0. Let's now prove that the condition 1 is satisfied. This is in fact the easiest part. Y is A of u phi equal to A of phi u. That's a symmetry condition, and it's very trivial to show this, that this condition is satisfied due to the definition of the bilinear form A of u phi, which was like this, and we now use that we can interchange the places of grad u and grad v in the integrand, due to the fact that two vectors, when we are taking the product between them, the scalar product, it does not matter in what order we do this. So then we easily obtain that this bilinear form is symmetric. So this was no problem at all. It's a little bit more tricky to show the second property. And the second property was devoted to the continuity of the bilinear form. And the continuity, in mathematical terms, it was given by this condition, that the absolute value of A of phi v for any pair of functions phi and v should be less than some positive constant c1 multiplied with these two norms. And this should be for any phi and v in the Hilbert space V, which is in our case equal to the Sobolev space W0. So, well, we are going to show that this condition is satisfied. And in order to use this, to show this, we have to use the Schwarz inequality. This is rather general. Very often that we need to use Schwarz inequality to prove condition 2. And the Schwarz inequality took this form, as we remember, and we are going to use this to show the property 2. Let us just remind you that the norm of phi is now equal to the square root of the sums of these two integrals. So let's have this in mind. Okay, when we are trying to prove the condition 2, let's start just with the left side here. The left side here, and write it out. We know that this is given, the A of phi v is given by this integral, and we are going to estimate the absolute value of A, which is given like this. In fact, here should be it's equal here, but it doesn't matter for our purpose. And this is, of course, by using now the Schwarz inequality, replacing grad phi, replacing u vector with grad phi, and w vector with grad v, we obtain this inequality. So this is exactly the same as the Schwarz inequality, just by replacing these two vectors with grad phi and grad v. Then we obtain this inequality, and using that lambda is a strictly positive function which is larger than some lambda minus, we obtain this. Here we have just replaced lambda is less than lambda plus. So this is the maximum value of lambda. So lambda can generally be some function which is dependent of the space variable, but now we have reduced the problem so that there is only a dependent in the constant lambda plus. And this constant we therefore can take out of the integral, and we obtain easily this. So lambda plus was taken out of the integral, in front of the integral, because it was a constant, and then we take the square root of this lambda plus, which we have done here, and the same for this guy. So multiplying these two numbers with each other, we just get lambda plus multiplied with the product of these two square roots. And you see here now we are very close to the norm of phi here. Just go back. It's important to see what we are doing here, because we know that the norm of in the Sobolev space. Let me show you this norm. We must have this in mind. So what we have now, we have this part of the norm, but we do not have this part of the norm. But now we know that this integral must be larger than the integral when we have removed this part. So what we just do here is to add this part. So if we are adding this part in the square root, we just get a larger number. Therefore we have this inequality here. And we do the same on this square root. We just add this integral of v square. And the reason for doing this is just to get the norm of phi and the norm of v here, the Sobolev norm. So now we have some constant lambda plus multiplied with the norm of phi and the norm multiplied with the norm of v. And this is in fact exactly the same as we need to prove in condition 2. We have now proved, we started with the absolute value of this bilinear form A, and I've proven that this is less than this. So choosing C1 equal to lambda plus, we obtain that the condition 2 is satisfied. So in fact this was not so difficult. It's difficult to do this the first time, but when you have considered several other examples of this, you will learn how to do this. On the exam, the students usually pass this thing very easily.